Okay, a little bit puzzled because I'm looking at non-restoring division, and that's fine because I've used that in the lab to make a division algorithm in hardware. So what you do is basically you start with the algorithm, say that the remainder is x, which is the divisor, and then you use some rule to get all the quotients, which is finally is the result. Now you can see that this is in signed digit form, so it's not you can't press it in human readable. The reason for using signed digits is to get to break the carry chain. Carry chain is something that causes long delays if the operand is long. The operand is the number you are dividing with, so or it's the number that you are working on in binary form. So if that's a 32-bit, well, then you have a 32-bit carry chain. So with signed digits you can break it up. You can use technique. So it's another number form, number system. Anyway, so that's okay. But then, to speed up the result even further, to converting to 2's complement, there's something called generating a 2's complement quotient on the fly. And that's very easy. You just shift the given number one bit to the position to the left, then you complement it, and then you shift 1 into the least significant position. So what you get, it was 0.P1 and so on, but instead you shift everything this way, you invert or you complement. This means 1 minus the binary digit, then you get the opposite value, and then you shift in 1. So that's okay, no problem. But then you have to, then I'm looking at the proof, and I'm a bit puzzled. I can get down here, but for me it's very tempting to put this 2 minus 1 into that index, which you can see I goes from 2 to m instead of 1 to m. So for me that was very tempting, but no. What it says instead, the book says the last term equals 2 minus 1 minus 2 powered by m minus m. And you can see you don't have that much in your sum anymore here in the equation. You only have the sum with the q quotient bit in it. But here you can see you have 2. So what it's basically saying is that the last term, which is this, I used half an hour to find out what that was. I have to read the book more carefully, I think. So it says that the sum of this is the same as this. And I can't see that directly, but when I do it graphically, it's not that bad actually. So, but I can't see it mathematically how that works. So now, if you look at it, the sum of 2 powered by minus I, these are like half. So it says that this sum is the same as 2 minus 1 plus, minus 2 powered by minus m. And what I see here, this is what I see. I see that the sum is the same as the first term, 2 minus I, you know, I starts at 2, therefore this is the first term. And you have this second term, which is the next I, which is 3, and then so on up to 2 powered by minus m, which is the last term, right? So to make it a little bit easier, I set m equals 4, so it doesn't go up to some generic m. So it makes the sum a little bit easier here, as you can see. 2 minus 2, 2 minus 3, 2 minus 4. 2 powered by minus 2, 2 powered by minus 3, plus 2 powered by minus 4. Sorry, I can't speak anymore. So, and this is also the way you calculate the value. I forgot to say that. Okay, maybe I should start over again. Okay, sorry about that. Sorry for going so fast, but the proof, what you're actually proving, is that this number here, when you substitute that with the q values, then the value of that binary representations, because these are just zeros and one in the positions here. So what you're proving is that you get q, right? So if you get q, then the value is the same as q. So let's get back. So just show you, for example, if you have the binary value 110, that's the same as 2 powered by 2 times 1, that's the 1. And then the next position, 1 times 2 minus 1. And then the last one, 0 times 2 to 0. So this is the way you find the value of a binary number. It's very easy. 4 plus 2 equals 6. So this is 6, so that's okay. But this is not what we're looking for. So I try to solve this graphically. So 2 powered by 0, that's the whole, that's 1. So I think the whole rectangle here is 1. 2 to the power of minus 1 is half. So that will be half of this. 2 to the power of minus 2, which is the first term, that will be this part of the square. So that's the half of the half. Then there's plus 2 minus the power of 3, which is half of the half. So that will be this part, alright, a half of the half. So that will be this part. And finally 2 to the power of minus 4, which is half of that again, which is here. So you can see what we are having left. If you want to try to get from this to this, which the book states is the same, well, then I can see it actually, because this was 2 to minus 1, the whole thing, or the whole half. And then if you then take the whole here, then you have this part left, which is too much. So you subtract 2 minus 4, which was, since this part here is 2 minus 4, then this one must be the same, because it's half of that. So yeah, so, and then if you say that minus 4 is the same as m, if we assume that, then you can see, since we start with m equals 4, yes, then we can say that this is true. So yeah, I thought that was a bit something, maybe some math I'm missing in my mind. So, but it was a little bit cool. So